Welcome to The Explainer. Today we're diving deep into hydrology. And that's really just the science of water, the stuff that literally moves, shapes, and sustains our entire world.
All right, let's jump right in with a question that, well, it really gets to the core of why any of us should care about hydrology. Think about it. Almost all of the water on Earth is salt water. So where in the world does the fresh water we all need to survive actually come from?
So to figure that out, here's our game plan for today. We're going to look at our planet's water engine, check out the global water budget, see how hydrology works as a system, and then get into the language of models and how to choose the right one. First up, our planet's water engine. Let's get a handle on the massive, non-stop process that powers, well, everything. So what is hydrology really? Well, it's not just about rivers and rain, you know. It's the science that follows every single drop of water on its incredible journey. A journey we call the hydrologic cycle, which is basically this endless, epic loop between the Earth and the atmosphere. And this cycle, it really has no start or finish. It's just a continuous journey. You've got water evaporating from oceans and land, it gets transported up into the atmosphere, condenses into clouds, and then comes back down as rain or snow. From there, some of it gets intercepted by plants, some soaks into the ground, that's infiltration, some runs off into rivers, and some recharges the groundwater. It's this constant, beautiful exchange. Okay, so that's the process. Now let's talk numbers, because the scale of this whole thing is just mind-blowing. Let's look at the global water budget. And when you look at where all the Earth's water is, one thing just jumps out at you: the oceans. I mean, look at that, 96.5%. It's basically the whole pie. Almost all of our planet's water is salt water, which leaves this tiny, tiny sliver for everything else. Okay, so now let's zoom in on just that tiny sliver of fresh water. And guess what? We find another surprise. Most of that isn't even accessible. Almost 70% of it is locked up as ice and snow at the poles. Another 30% is deep underground as groundwater. So the water you actually see, the stuff in lakes and rivers we rely on every day, it's a shockingly small fraction of the total. And this right here, this is the critical takeaway. That number, 0.006%, that's the percentage of Earth's fresh water flowing through our rivers at any given time. 0.006%. It's wild. The very rivers that have sustained civilizations for millennia are just a tiny, fragile thread of water, which makes them an unbelievably precious resource. So, this water is always on the move, right? But how fast does it move? To figure that out, hydrologists have this really cool concept called residence time. It's pretty much what it sounds like. What's the average amount of time a water molecule hangs out in one part of the cycle before moving on? And the math behind it is actually super straightforward. To find the residence time, or TR, you just take the total amount of water you have in storage, which we'll call S, and you divide it by the flow rate in or out, which we'll call Q. Simple as that. Okay, let's put this into practice. Take the atmosphere. We know it holds about 12,900 cubic kilometers of water at any given time. That's our S. And we know that about 577,000 cubic kilometers rain out of it every year. That's our Q. So you do the math, S divided by Q, and you get about 8.2 days. And that's it. A water molecule only stays in the atmosphere for a little over a week on average. This super fast turnover is a huge reason why forecasting the weather more than a week out is so incredibly hard. Okay, so obviously trying to track every single water molecule on the planet would be impossible, right? The whole cycle is just way too complex. So to make sense of it all, scientists have to simplify. And they do that by thinking of hydrology as a system.
And what's a hydrologic system? Honestly, the best way to think about it is like a black box. You don't have to understand every single gear and wire turning inside. You just draw a boundary around it, and then you carefully measure what goes in, the inputs, and what comes out, the outputs. The system is just the magic that happens in between.
A watershed is the perfect real-world example of this. So a watershed is just all the land that drains water to a single point, like a river. In this system, the input is the rain that falls over that whole area. The black box itself is the landscape, the soil, the slopes, the little tributary streams that channel the water, and the output, that's the river's flow that you can measure right at the bottom of the watershed. Okay, so we have inputs and outputs, but how do we connect them? How do we describe what that black box is actually doing to turn the rain into river flow? Well, for that, we need to speak the language of models. And don't let the math scare you. At its heart,
A hydrologic model is really just a recipe. It's an equation that says the output, let's call it Q for streamflow, is a result of the input, we'll call it I for rainfall, being transformed by some process. That process, that recipe, is represented by that funky symbol omega. The model is the recipe.
Let's look at a simple example. This is called a linear reservoir model. It's built on just two core ideas. First, the storage principle. It assumes that the more water is stored in the system, the faster it flows out. Makes sense, right? Second, the continuity principle. This is even simpler. It just says that the change in how much water is stored is equal to what comes in minus what goes out. You put those two simple ideas together, do a little bit of calculus, and boom, you get that one equation at the bottom. That equation is the model. It directly connects the input to the output. But obviously, the real world is a lot messier than that simple model. So hydrologists have a whole toolbox full of different models. And choosing the right tool for the job really comes down to asking a few key questions.
First question, how much randomness are you dealing with? If your system is pretty predictable, you can use a deterministic model. Put in the same input, you get the same output every time. It gives you a forecast. But for something messy and unpredictable like rainfall, you probably need a stochastic model. This one embraces the randomness and gives you a probability instead of a sure thing. It makes a prediction.
The next big choice is all about space or scale. Are you looking at the big picture or the tiny details? A lumped model is the big picture. It treats the entire watershed like one single unit, averaging everything out. It's simple and fast. But if you need to know what's happening in specific places, like what's the soil moisture on this particular hillside, then you need a distributed model. It breaks the whole area into a grid and calculates things for each little square, giving you a much more detailed map. So, models, equations, systems. Why does any of this really matter? Well, it matters because it's the key to understanding our future and the future of our water. And here's the thing. For most of history, we were just observers of this giant water cycle, but not anymore. The quote here says it all. Human activities gradually encroach on the natural water environment. Our actions, paving over landscapes, building massive dams, irrigating farmland, these aren't small things. We are now a major force, a significant input that is actively changing how the whole system works. And that leaves us with a really big question, a really important final thought. Our climate is changing, our landscapes are changing because of us. So how do our models need to change to keep up? The science of hydrology isn't just an academic subject anymore. It's absolutely essential. Because we now have this incredible responsibility, not just to understand the planet's water engine, but to manage our own role as one of its most powerful drivers.